Akleek Island, approximately 75 miles wide. It lies 700 nautical miles from the North Pole and is uninhabited except for occasional polar bears. At 6 a.m. on the 5th of September, wind on the island was from the southwest at 3 knots. Temperature was 26 degrees Fahrenheit, and barometric pressure was 29.4 inches of mercury. Broadcasts of weather are automatically made from Axel Heiberg every 3 hours, 24 hours a day. It is a free contribution to the world community. For across the wastes of the Arctic, the weather begins that eventually sweeps down into the backyard of half the world. If we are ever to learn about the makeup of the storms in the Northern Hemisphere, we must learn it here. But weather information on the Arctic is scattered and fragmentary. A year-round automatic weather station on Axel Heiberg will fill in some of the gaps, will chart the wilderness of Arctic weather. The broadcast originates with a small weather station installed on the island on the 17th of August, 1961. Power to run the recording and transmitting equipment comes from atomic energy. The specific power source is the radioisotope strontium-90, which gives the generator a design life of 10 years. But strontium-90 seems at first glance a very unlikely isotope for any such peaceful use in society. It has a half-life of approximately 28 years and emits intense ionizing radiation. Even though the radiation decreases with time, shielding must be provided for decades. Strontium-90 is mainly produced as a byproduct of reactor operations. Many radioisotopes are produced in this way that we cannot fully use at present, but which must be safely controlled. By 1961, large quantities of strontium-90 and other radioisotopes were being handled as waste from reactor operations. 4 major facilities of the Atomic Energy Commission have acquired extensive knowledge of waste disposal and storage. The Hanford Atomics Products Operation in Washington State, the Idaho Chemical Processing Plant, the Savannah River Plant in South Carolina, and the Oak Ridge National Laboratory in Tennessee. Generally, 3 major methods of reactor waste handling are used at these facilities: radiochemical processing, underground storage, and soil retention. Therefore, storage differs at various sites. Methods of removing the heat generated during decay of the radioisotopes also differ. For example, radiochemical processing is conducted in the Fission Product Development Laboratory at Oak Ridge. Valuable isotopes for use in medicine are recovered in this way. Industry uses isotopes for many applications, including gauging and radiography. In agriculture, animal metabolism studies with tracer quantities of isotopes have increased milk production. Another technique to reduce storage facilities for very low-level waste is that of soil retention. After acidity adjustment and concentration meet AEC health and safety requirements, low-level wastes are discharged into the soil of controlled areas. But high-level radiation waste must be safely stored in large underground tanks. They are generally metal tanks holding up to 1 million gallons of liquid waste. Cost estimates on this method range from 30 cents to $2 per gallon, but it is still the safest and cheapest way to contain high-level wastes. But storage is an unproductive end for energy contained in radioactive waste. Therefore, AEC's Division of Isotopes Development awarded a contract in 1958 to Martin to study the use of strontium-90 as a heat source for small-scale generation of electricity. The job was to convert unproductive quantities of strontium-90 into a useful compound for peaceful applications. The development of a remote automatic weather station was to receive particular attention. Strontium titanate was chosen from many compounds studied because of its extreme insolubility in fresh and seawater. In freshwater tests, strontium titanate was undetectable, while only 0.3% of strontium titanate dissolved in natural salt water after 2,400 hours testing at 150 degrees Fahrenheit. Compound studies also demonstrated that strontium titanate has high strontium density, that it is stable at temperatures far above operating conditions, and it is resistant to thermal stress. Strontium-90 for the weather station was shipped from Hanford Atomics Products operation to Oak Ridge in specially designed casks. The isotope was processed in the Fission Product Development Laboratory. The first major step is a wet chemistry process. Strontium is finally precipitated as the carbonate in the presence of titanium dioxide. The precipitate must be filtered and dried. Wet chemistry is followed by calcination. The compound is withdrawn from the filter and placed in a furnace to decompose the carbonate. This will give us a powder to compact into pellets. Sintering converts the discs of strontium titanate into a ceramic form. Only 1 pound of fuel is required for the 5-watt generator used in the Arctic. Once loaded, the fuel capsule or container must be welded tight. Some 17,500 curies of strontium titanate have been placed in the capsule. The capsule, in turn, will be loaded in a thermoelectric generator. A thermoelectric generator is a device for the direct conversion of heat into electricity. It makes use of a principle discovered by Seebeck. He showed that a continuous electric current would be produced when a thermocouple consisting of 2 dissimilar metals connected in a closed circuit has its junctions maintained at different temperatures. Thermocouples had previously been used for temperature measurement, but it was the development of thermocouples fabricated from semiconductor materials such as lead telluride that made practical the production of electrical power by this principle. The weather station generator uses 60 such thermocouples made from lead telluride. The heat produced by the decay of strontium-90 maintains the hot junction temperature. Cylindrical in shape, the generator is 20 inches high and 18 inches in diameter. The generator weighs 55 pounds and is shielded by 4.4 inches of lead weighing 1,600 pounds. The fuel is contained in a single capsule made of Hastelloy C. It has a design life of 500 years. The capsule is housed in a cylindrical sleeve, also made of Hastelloy C, which serves as the heat junction. The thermocouples and a heat sink complete the generator design. The generator powers all of the automatic equipment of the weather station. The weather station, apart from the generator, consists of the data processing equipment, the measuring systems, timers, chronometer, and the 2 single sideband transmitters. A 24-volt battery is constantly being recharged by the generator. The station transmits 4 basic weather conditions: temperature, barometric pressure, wind direction, and average wind speed every 3 hours. On receipt of a start signal from a master timer, the data processing equipment reads and stores data from all instruments. It generates the station call letters, VA, converts the data to a binary code, and sequences it to the transmitters. Broadcasts can be picked up at a receiving station several hundred miles distant. Decoded, the weather information can be relayed to major meteorological centers on the American continent. Acceptance tests on the generator and station equipment were run from May through 10 July '61. In the laboratory, an electrical heater powered the generator during initial tests for 35 days. The loaded generator was then received from Oak Ridge National Laboratory, and the complete weather station was erected at the contractor's facility for a full-scale checkout. The generator went underground on the 1st of June and powered the station for 40 days. It broadcast successfully during this time to a receiving station in Washington. The first Strontium-90 weather station was ready for active duty in the Arctic. Ahead of it lay a journey of almost 4,000 miles, made possible by joint Canadian-United States teamwork. The station was first trucked from Baltimore to Montreal, and on the 24th of July, it was loaded on board the Canadian icebreaker, the John A. Macdonald. As the Macdonald made its way north, the Royal Canadian Air Force flew an international weather team into the last outpost of northern Canada, Resolute. From here north, things get a little primitive. At Resolute, the first job was started. Antennas were erected for future transmissions. As they went up, the Macdonald swung into the harbor with the weather station and the equipment to complete the receiving station. Men and supplies were loaded on the 12th of August. By noon the next day, the small task force was underway. The Macdonald set its course from Resolute around Devon Island, through the narrow passage of Hell's Gate, bound for Graham Island, Northwest Territory. But, as we shall see, problems developed at Graham, and the Macdonald was forced to turn further north. It landed the task force at Sherwood Head on the southern tip of Axel Heiberg Island. As the Macdonald skirted Devon Island on the second day, it began running into floating ice. A helicopter flew out regularly to scout a passage ahead. Glaciers were spotted on the north coast of Devon the second day out. Ice thickened. At Hell's Gate, it was running solid at depths of 4 to 6 feet. As the ship approached Graham Island, the ice closed in. It was now 8 feet deep. After fruitless searching, the helicopter returned to the ship. There would be no passage to Graham Island on this trip. A decision was made to proceed to an alternate site at Axel Heiberg, which had been selected earlier for just such an emergency. This time, the weather and luck held. A clear passage was found into the harbor, and as the Macdonald made its way into the final stages of the journey, the two helicopters landed the advance party to begin survey of the site. It was 6 p.m., 15 August. Luck seemed to smile on the party. They found the permafrost level at 4.5 feet. Large-scale blasting was unnecessary. Captain Cuthbert, skipper of the Macdonald, now ordered his entire crew to pitch into the job. No one had asked for their help, no one had expected it. But it meant that 30 Canadian sailors and 11 regular members of the task force, 41 strong backs in all, began unloading with a vengeance. A bulldozer served as the all-purpose vehicle on the ground, hauling supplies from shore to site. The first of the 3 antenna masts was up within 24 hours. The mechanics of the job continued to go smoothly, and the telemetry package was first checked out using 4 6-volt lead-acid batteries. Within 30 hours, ship-to-shore communications confirmed contact with Resolute. We were ready for isotope power. The strontium generator was connected, the chronometer was synchronized, and the barometer set. The assembled station was lowered into its housing in the ground, and soil bulldozed around it. Only the top and snorkel tube protecting the antenna wiring remained above ground. The generator will maintain an average temperature of 70 degrees within the station, protecting the electronic components from Arctic cold. The station was now on its own, with a warning to unlikely Arctic visitors. The last of the installation party returned to the ship. There they awaited word from the receiving station at Resolute to tell them whether or not the job was done. The wait was short. Resolute received the first broadcast. Decoded, it read, wind at 2 knots from the northeast, temperature 38 degrees Fahrenheit, barometric pressure 29.92 inches. Captain Cuthbert came out of the radio shack with the return wire just 48 hours after he had landed the advance party on the island. And the first nuclear weather station in the Arctic, or anywhere else for that matter, was in business. There was plenty of credit to go around before everyone decided to get some sleep. The Arctic station is not the end of the journey, or the end of peaceful use of strontium-90. Vast stretches of the sea, some 3/4 of the Earth's surface, offer an ideal environment for remote automatic devices powered by radioisotopes. SNAP 7A generators for light buoys and SNAP 7B units for fixed navigational beacons powered by strontium titanate are well advanced into hardware. These units only scratch the surface, but they indicate the wide breadth of potential applications. Buoys with radioisotopic power sources will increase their service life many times. Older maintenance practices will be radically simplified. For example, as many as 72 wet cell batteries are used in some buoys. Just the recharging and handling of these buoys demand costly maintenance facilities. They are brought in from the sea and recharged every 6 months. If we substitute isotopic-powered systems for batteries, we will eliminate this type of maintenance problem. And of course, additional remote weather stations are a logical development. This is a SNAP 7C generator. It will power a companion weather station at the other end of the Earth from Axel Heiberg, going into operation at Little America Station number 5 near the South Pole late in 1961. Indeed, we need only a short look into the future to see that isotope power generators will use increasingly significant amounts of strontium-90. The AEC is turning its attention to other fission products, such as cesium-137 and cerium-144. As increasing quantities are put to use, we will enter a new era, an era where radioisotope waste will be transformed to wealth. Strontium-90 becomes a servant of the nuclear age.
This is National Educational Television.
Peacetime atomic energy has found its way into the animal kingdom. Here it helps answer important questions relating to our daily living. How does food containing radioactive materials affect animals? What effect, if any, has an atomic processing plant on the vegetation and livestock in its area? How are certain foods used in the growth of animals important to the American economy? Experimenting with sheep, scientists at AEC's Hanford Works are gathering vital information that safeguards the important lamb and wool industry in that area. Since waste products, such as radioactive iodine from chimney stacks at atomic plants, often settle on soils and vegetation eaten by sheep, it is important to know the exact effect this has on them. Sheep are fed food pellets containing varying amounts of radioactive iodine in addition to balanced diets of alfalfa and grain, and are then tested. This helps biologists and doctors, and it aids engineers in the design of future atomic plants. The pans are carefully monitored after each feeding. Radiation instruments are used to measure to what extent the material is being retained in the bodies of the sheep. Since much of the radioactive iodine is deposited in the thyroid, it is this area that is first tested. Also, at regular intervals, blood samples are taken from the sheep. This permits the scientists to determine the effects of radioactive products on the blood cell count and the chemical constituents of the blood. As we said, the sheep are fed varying amounts of radioiodine, ranging from quite minute to fairly appreciable quantities. Thus, the tests will give much valuable data. This technician is preparing the blood samples for a white cell count. She dilutes the blood with a special fluid and puts a measured amount into a pipette. The pipette holder will be kept in constant motion to ensure proper mixing. The results of these experiments will furnish valuable information both to the medical profession and to the livestock industry. The next step in the count is to remove the pipettes from the shaker, place a sample of the blood on a plate, and by means of a microscope make the actual count. The offspring of the sheep will also be studied for several generations to determine the physical changes that may have been caused by the effect of radiation on the first group of sheep. Results to date, certain knowledge that we are not harming the animals foraging near atomic installations, and valuable data for engineers who will build the new atomic plants in this age of the atom. Now the blood count has been completed. It will be tabulated and recorded for future reference. One of the mysteries scientists have been attempting to solve is the way in which the hen absorbs through her food calcium and phosphorus and builds them into the various components of the egg. Studies at the University of Tennessee are breaking through this barrier of knowledge. This hen is receiving a feeding of radioactive calcium and phosphorus, which will find their way into the egg. But this is a very special egg. The calcium and phosphorus in it give off little bursts of radiant energy that can be traced by radiation counters. The egg is separated into white, yolk, and shell. Each of these components will be studied individually to note the amount of calcium and phosphorus that have been made part of their construction. These experiments are aimed at gathering vital data about eggs, universal food products. Perhaps the knowledge may lead to better methods of feeding hens so that someday we may have a bigger production of more nutritious eggs. Such fascinating research is attracting more and more young scientists and technicians into the atomic energy field. The separated parts of the egg will next be placed in a muffle furnace for drying and ashing. The temperature of the furnace is kept at a constant level, and the drying process takes 2 days. The overall atomic biological research program includes both plant and animal work, and it is hoped that it will result in major gains toward understanding plant and animal life processes and soil-plant relationships, which combine to give you improved agricultural production. But let's get back to our egg, which has now been thoroughly ashed. Acid is added to dissolve the residue. After it is completely dissolved, it will be poured into a petri dish and placed under a radiation counter. This is just one of the experiments conducted at the University of Tennessee. Many radioactive materials are being used to learn how animals absorb certain elements and build them into bone and muscle, which then become food products for mankind. This particular count takes 4 minutes to complete and tells the scientist the amount of radiation in the sample. This helps to trace the course of calcium and phosphorus from the laying hen to the egg and in the continuing cycle to future generations.
The first specific evidence that radiation is carcinogenic dates back to the 90s. Carcinomas of the hands and other radiation injuries commonly afflicted the operators of unshielded X-ray machines. Adequate protective devices and safe procedures were gradually developed during the first half of the 20th century. Intensive research on radiation carcinogenesis has also developed. This research is becoming more and more important in understanding the causes of cancer. Not only are radiations carcinogenic, but some chemical compounds are carcinogens, such as dyestuff intermediates and other relatively common substances. The carcinogenicity of an aromatic hydrocarbon can be demonstrated. By means of a camel's hair brush or a medicine dropper, 3,4-benzpyrene is applied to the skin of a test animal. A period of latency follows. When tumors appear, they are readily identified as papillomas or carcinomas. Histological examinations confirm such diagnoses. Subcutaneous injections of another chemical, 20-methylcholanthrin, also produce tumors that can be recognized by inspection. Ulcers of the skin may form or tumors may develop. The malignancy of this sarcoma is seen at autopsy and through histological examination. Such experiments with chemical carcinogens are important. Increased attention in cancer research is also being given to radioactive carcinogens. This research is not only of practical importance in its own right, but contributes further to an understanding of cancer. A typical experiment with a radioactive carcinogen begins with the shaving of a test animal. Later, this animal will be subjected to the radioactivity of strontium-90 beads contained in one of these jackets. There are 10 radioactive beads mounted on the inside of each jacket. A jacket is strapped on the animal and held in place for 48 hours. For mice and rats, a period of latency of about 100 to 200 days follows. The equivalent in human time is about 10 to 20 years. Control animals are also required in these experiments. The beads in the jacket strapped on each control animal are non-radioactive. Radioactive beads release beta radiation, a kind of radiation also produced by atomic explosions. To understand the nature of such radioactive carcinogens, it is well to begin with the atom. The atom pictured here is the simplest kind in existence, hydrogen. Its center or nucleus consists of a single proton positively charged. Its single orbit contains one negatively charged electron. An isotope of hydrogen is tritium. Besides the proton in the nucleus of each tritium atom, there are two neutrons shown here as blue ovals. Each neutron may be thought of as consisting of a proton closely packed with an electron. Therefore, the net charge of a neutron is 0. Tritium is the simplest radioactive atom known today. Radioactivity is the property of a nucleus to change into the nucleus of a different element. For example, tritium changes to helium-3 by a process which begins with the loss of the electron from a neutron. Such an electron expelled from the nucleus is a beta particle. Beta radiation is a stream of such particles. Here, the loss of an electron leaves the nucleus with a total charge of +2 and the orbit with a charge of -1. To balance these charges, a second orbital electron is acquired. The resulting atom is helium-3. Helium-3 with charge 2 is a rare isotope of natural helium, helium-4. If through atomic disintegration or by artificial means, a helium atom loses both of its orbital electrons, the nucleus that remains is an alpha particle. A stream of alpha particles is commonly called alpha radiation. This drawing represents a more complex atom, sodium-24. In this and some other kinds of atoms, the expulsion of a nuclear electron is accompanied by the emission of gamma radiation, another important kind of radiation. Gamma radiation, for all practical purposes, is identical with X radiation. These three kinds of radiation, alpha, beta, and gamma, are the radioactive carcinogens most commonly used experimentally. But there are others, such as ultraviolet light, neutrons, and protons. When a radioactive carcinogen, such as one of the radioactive beads in a jacket, impinges upon a bodily surface, external radiation takes place. Surface irradiation may also result from the impingement of radiation upon an inner body surface, following imbibition of insoluble radioactive particles in water, or inhalation of radioactive dust particles. In this instance, we show the effect of radioactive particles that reach the stomach through drinking water. The radiations first penetrate epithelial tissue and may continue until they reach mesenchymal tissue. The damage to cells of the body resulting from surface radiation varies in depth with the kind of radiation. Alpha particles are so big that they readily collide with other particles. So alpha radiation has a very short range of between 20 and 50 microns, as symbolized here. Some beta rays, too, have a rather short range because of their low energy content. But, as indicated here, most beta rays penetrate the skin for a distance of a few millimeters. Compared with either alpha or beta radiation, the penetration of gamma and X-rays is much deeper. Here, gamma rays are symbolized. Many of them pass completely through the neck of a human, as shown in cross-section. In contrast with such examples of surface irradiation, internal radiation takes place when the source of the radiation itself is deposited in tissue. This may be achieved by absorption or by mechanical means, as in the subcutaneous injection of a radioactive substance in solution. The source of the radiation may also be deposited in tissue. In this laboratory example, a radioactive bead is being embedded in the posterior lobe of a rat's liver. The well-known affinity which parts of the body have for naturally occurring elements applies also to the radioactive isotopes of these elements. Radiosodium, for example, distributes itself throughout the body, just as does sodium. Radiostrontium is bone-seeking, as is strontium. and radioiodine seeks out the thyroid, as does iodine. Most carcinogenic radiations produce ionizations. Radiation produces ionization by knocking orbital electrons of molecules out of their orbits. This kind of ionization needs to be clearly distinguished from the ionization which occurs naturally in nature. For example, in nature we say that each 600 million molecules of water, natural water, contain one hydrogen ion, H, and one hydroxyl ion, OH. We have reference to natural ionization also when we describe the ionization of sodium chloride in solution to produce sodium ions, NAs with plus charges, and chloride ions, Cls with minus charges. In contrast with this kind of ionization, radiation ionization causes molecules to decompose into uncharged atoms and radicals which then have far-reaching effects on other molecules with which they come into contact. When water undergoes radiation ionization, free atoms of hydrogen and free hydroxyl radicals are produced. First, a gamma ray dislodges an electron in one water molecule, leaving behind a water ion with a positive charge. Being unstable, this water ion breaks up into a hydrogen ion, H with a plus charge, and a hydroxyl radical, OH. The radical OH is an oxidizing agent. Meanwhile, the electron from the first water molecule combines with another water molecule. This action produces a hydroxyl ion, OH, with a minus charge, and a hydrogen atom, H, which is a reducing agent. We know that the biochemical system of each cell in the body is an enormously delicate balance of oxidations and reductions. When oxidizing or reducing agents produced by ionizing radiation upset this balance, the cell becomes sick. The oxidizing effect of the hydroxyl radical on alanine, a common amino acid in the body, illustrates the action. The hydroxyl radical causes the alanine molecule to break up into acetaldehyde, ammonia, water, and carbon dioxide. The oxidizing effect of the hydroxyl radical and the reducing effect of the free hydrogen atom are both destructive. Besides this, the strongly acidic hydrogen ion and the strongly basic hydroxyl ion can do severe local damage to the normal acidic and basic balance of the cell's biochemical system. The human body is subject to a certain negligible amount of ionization at all times. It is produced not only by cosmic rays, but by minute quantities of radioactive potassium, carbon, and radium, usually found in the body. No one can predict when a given radioactive atom will explode, but given a population of radioactive atoms, we can predict statistically how rapidly they will lose their radioactivity. For example, here are symbols representing radioactive sodium atoms. Their half-life is 12 hours, indicated by one complete turn of the hour hand. That is, by the end of any 12-hour period, half of all the radioactive sodium atoms change to non-radioactive atoms. In the next consecutive 12-hour period, half of the remaining radioactive atoms change, and so on during each succeeding 12-hour period. Half-life varies enormously among the radioactive elements. For some, it is less than a second. For others, it is centuries. The production of cancer by ionizing radiation depends upon the location and density of the ionization produced, and upon the duration and amount of exposure. Using strontium-90 radiation, carcinogenesis has been achieved only when a larger than permissible dose has been administered. 1,500 microcuries of beta radiation are used in the jacket applied to the rat. Beta radiation can penetrate tissue for several millimeters. It therefore penetrates the cornified layer of epithelium and injures the epithelial tissue. The first observable effect is erythema. Distinct incidences of erythema correspond in position to the radioactive beads which were strapped on the rat's back. If the dosage is light, the erythema behaves like the erythema associated with non-radioactive burns. Capillaries finally shrink, and the skin returns to apparent normality. In contrast, a large dosage is followed by ulceration and epilation, as in the case of severe non-radioactive burning. As in injury from non-radioactive burns, this ulceration is due to cell destruction. Cancer is not necessarily a consequence of radiation burn. Normal healing processes may restore tissue, and scar tissue will result, accompanied by permanent epilation. In a large percentage of experimental animals, this represents the end result of the organism's reaction to irradiation. When normal animals are irradiated, the effects are not apparent for about 3 months. Then, certain of the irradiated animals develop malignancy. Cells that have been damaged start behaving cancerously. The cell growth is abnormal and uninhibited by the discipline of normal mitosis. Wild epithelial cells grow down into the connective tissue. The vascular system is unable to cope with the abnormal demand, and cells near the surface are starved to death, with the consequent development of ulceration commonly associated with carcinoma. Experimental animals reveal the effects of irradiation. The carcinomas induced in rats by external beta radiation range considerably in size. In some, ulceration is pronounced. The tumor may have considerable depth. As starved tissue is discarded, a crater like this may develop. Biopsied for histological examination, such a tumor is clearly seen to be malignant. The wild epithelial cells have grown down into the connective tissue. The penetrability of beta radiation makes damage to the underlying connective tissue possible and likely. A sarcoma developing in this tissue will either remain subcutaneous or will grow through the epithelial wall, weakened as it has become by the immediate destructive effect of the radiation. This experimental animal has a subcutaneous tumor which proves upon biopsy to be a sarcoma. Not all sarcomas, however, are subcutaneous. Here, for example, is a sarcoma that has become exposed. Sections obtained upon biopsy from this exposed tumor reveal this appearance under the microscope. Such tumors are unmistakably sarcomas, induced by beta radiation. Compared with beta irradiation, external alpha irradiation of any cornified epithelium does little if any damage. The inner surfaces of the body, however, can be severely damaged by alpha irradiation, such as results from the inhalation of an alpha-emitting substance. The substance that is emitting alpha rays moves with the airstream into the lungs. In this example, some particles of the radioactive substance reach the area indicated by the arrow. Cutting the bronchus below the arrow reveals the section of the bronchus to be observed. In this case, particles of the alpha-emitting substance reach epithelial tissue. When this occurs, great damage may result. Radiation causes damage to the cells by ionizing the molecules out of which they are made. One of the results of such ionizing radiation of the molecules is an abnormal growth of the affected cells. The division of such cells proceeds at an accelerated rate, and cancerous tissue begins to form. Although the penetrability of surface alpha radiation is slight, it is ample to cause severe damage to tissue. Likewise, internal alpha radiation from small amounts of radium, either from industrial or therapeutic exposure, can seriously damage bone. This X-ray shows an example of a bone damaged by radium. 16 years ago, this patient received an injection of radium for therapeutic purposes. Since then, the radium has caused a fibrosarcoma to develop. Today, we are able to demonstrate the presence of radium in the bone. After an operation, a section of the bone is photographed by radioautography. This radioautograph reveals the tracks of alpha particles, thereby clearly indicating that the sarcoma was caused by radium irradiation. The extreme penetrability of hard X-rays and gamma rays makes them carcinogenic to all parts of the body. Whatever the kind of radiation, its effects depend upon the dosage, the length of exposure, and the individual's susceptibility to cancer. The induction of cancer after high-level exposure to carcinogenic agents is fairly probable. After low-level exposure, the probability is slight. Equipped with the facts that are known today about radiation and the facts that are within reach of research workers, the medical profession will be able to respond confidently to whatever challenge the future may hold.
In mid-1954, the Atomic Energy Commission and Atomics International entered into a program to study and improve the technology associated with the sodium graphite type of nuclear reactors. The technical feasibility of this approach to economical nuclear power is experimentally demonstrated through the construction and operation of the sodium reactor experiment. The facility is located in the Santa Susana Mountains, 30 miles northwest of downtown Los Angeles. It incorporates a 20,000 thermal kilowatt reactor, having the basic design features of a full-scale central station sodium graphite reactor. Liquid sodium serves as the coolant and heat transfer medium. Graphite is used as moderator. The arrangement of major reactor components is shown by illustration. The stainless steel core tank is 19 feet deep and 11 feet in diameter. It is located beneath ground level. Surrounding the core tank is a cast steel thermal neutron shield, a secondary tank to maintain the sodium level above the fuel elements in the event of a core tank rupture, thermal insulation, a steel vault liner, and a concrete vault. An overhead view shows the graphite moderator and reflector units, which are contained in 119 canned assemblies. The inner 55 are pierced axially by coolant channels, within which the fuel elements may be suspended. Liquid sodium coolant flows into the reactor at the bottom of the core tank. From there, it flows past the hot fuel elements to an upper pool. To remove this heat, the radioactive coolant is pumped through a primary loop and returned to the core tank for recirculation. The heat from the sodium in the primary loop is transferred by a heat exchanger to a secondary loop, which is non-radioactive. The heat from the secondary loop can be exhausted to the atmosphere by a sodium to air heat exchanger, or it can be utilized in a steam generator. The steam drives a conventional turbo generator for the production of electricity. Output capacity is rated at 7,500 electrical kilowatts. The fabrication and testing of major reactor components for the sodium reactor experiment is shown in this film. The fuel elements for initial operation were made in the form of 7 rod clusters. Support is provided by a hanger at the top of each cluster. A spacer plate at the lower end permits individual expansion of the rods. To prevent the rods from touching each other or the coolant tube, the 6 outside rods were spirally wrapped with stainless steel wire. Each rod consists of a 6-foot-high column of 6-inch solid uranium slugs. A thin-walled stainless steel jacket encloses the slugs and is sealed at each end by a welded stainless steel plug. A closely packed array of hexagonal graphite blocks, canned in zirconium, forms the reactor moderator. Fabrication of the moderator units will be shown in detail. The blocks were machined from 300-pound logs. They were first rough cut, then smooth finish. Each operation required a single pass under the cutter. This graphite exceeds the extremely high purity standards established for reactor applications. No impurities of any significance can be measured by the conventional chemical or spectrographic methods. Personnel working with the graphite wore uniforms and gloves which were laundered in a boron-free soap. And all tools, gauges, and fixtures were washed with alcohol as insurance against contamination. The graphite was stored at all times in aluminum foil. The zirconium cans, which enclosed the graphite moderator blocks, were fabricated from 6 separate longitudinal panels. The formation of each panel was completed in a single break operation. This is a 60-degree bend. The formed panels were machined to the specified width. This operation was critical, since it determined the tolerance on the completed moderator can. After machining, the panels were cleaned by micro sandblasting, the final step before assembly. A heliarc welding stake was employed for longitudinal welding. The seams were fused together without the use of filler rod. This assured neater joints with a minimum of contamination. Dimples, which were rolled into the panels during fabrication, ensure a thin, flat channel between adjacent can walls. This space permits heat removal by the circulating reactor coolant. The bottom end caps were heliarc welded in place. Argon under pressure within the central tube provided an inert atmosphere behind the weld. Moderator can end cap welds were investigated through mid-1955. 10-inch sections of the cans were prepared for these tests. The object was to study the possibility of buckling or cracking of the head welds due to thermal stress, which might be encountered during reactor shutdown. The thermal stress was simulated in this test by mechanical cycling. The can was immersed in sodium and evacuated. Sodium temperature was maintained at 950 degrees Fahrenheit. Any break in the welds would be detected by a sodium leak indicator. Early failures were observed, which led to an improvement in head design. Later heads have survived cycling tests equivalent to nearly 8 years of operation in the sodium reactor experiment. The main purpose of the moderator can is to isolate the graphite from the sodium coolant A leaking can would allow absorption of sodium by the graphite, causing excessive neutron losses. Each can was sealed, evacuated, and all welds helium leak tested. The welds were also X-rayed to check for porosity and contamination. Any faulty portions were marked, re-welded, and X-rayed again. A horizontal graphite loading jig facilitates final assembly of the moderator elements. 3 graphite blocks comprise the moderator element for each can. A graphite indexing plug at the junction of adjacent blocks prevents rotation. The total weight of the complete canned moderator assembly is about 760 pounds. After loading, the top cap was welded in place and X-rayed, and the complete moderator unit given a final leak test. There are 4 control elements in the core located as shown diagrammatically in this overhead view. Each element is self-contained in a sealed thimble assembly, which extends from the top of the upper shield to a point just below the core. The poison column is made up of a series of 18 boron-nickel alloy rings suspended on a pull tube. The pull tube is raised and lowered by a motor drive system located just above the top shield. Studies were made to determine the optimum clearance between control rod rings and the tube within which they operate. An electrically heated graphite coil was employed to bring the test rings to SRE operating temperatures. Various ring sizes were tested to establish the best size for free movement and dissipation of the expected heat load. These rings were thermal cycled in another series of tests to investigate physical changes which might occur under operating temperatures. They were cycled 500 times for a maximum of 1,500 degrees Fahrenheit down to 700 degrees, with a gradient across the rings of 300 to 400 degrees. These tests indicated that the changes in size would be well within acceptance limits. A grid plate near the bottom of the core tank supports and locates the moderator assemblies. It was fabricated from type 304 stainless steel and is 1.5 inches thick. The smooth finishing of the moderator can spacer holes is shown here. A pedestal at the bottom of each moderator can fits into these holes to support the can and position it precisely. These holes space the lower ends of the moderator cans and fuel elements on an 11-inch triangular lattice. The core tank is 19 feet deep and 11 feet in diameter. Made of 304 stainless steel, it has a wall thickness of 1.5 inches. The bottom head was formed cold and specially heat treated to maintain the required close tolerances. Prior to fabrication, all material was ultrasonically inspected for internal laminations and voids. The sides of the tank were built of 3 ring sections, each welded in place. All welds were given dye penetrant and X-ray inspection. Surrounding the core tank is the thermal shield. Its function is to absorb most of the heat due to gamma rays and neutrons, and to protect the concrete shield from thermal damage. It was fabricated from 1030 carbon steel, melted in an electric steel furnace. The complete shield was made up of 7 individually cast rings. Each ring was fully annealed to remove stresses in the casting, and then was machined to the specified 5.5-inch thickness. The top ring is 29 inches high. The remaining rings are each 35 inches high. Outside diameter is 12.5 feet, with the tolerance held to a plus or minus 1/32 of an inch on both inside and outside diameters. To allow free expansion and contraction during reactor shutdown, these rings are not welded to each other. Stainless steel bellows seal the tops of the core tank and outer tank. They permit vertical expansion of the tanks, but prevent escape of sodium vapor and helium from the core area. The form for the rotatable top plug is made of type 405 stainless steel. It is filled with dense concrete 6 feet in thickness and shields the area directly above the reactor core. There are 81 small plugs and 4 larger plugs extending through this shield. These plugs are located to permit access for removal of any fuel element or moderator assembly within the core tank when the shield is rotated. Total weight with concrete and plugs is 75 tons. The sodium pumps are modified hot oil pumps designed for high temperature service in oil refineries. The principal modifications consist of vertical mounting and the addition of frozen sodium seals at the shaft and at the case. This pump will deliver 1,285 gallons a minute against a 130-foot sodium head. The intermediate heat exchangers employ a shell and tube counterflow arrangement designed in a U shape. This configuration conserves space and minimizes thermal stresses. All components requiring special cooling are served by a system which circulates liquid tetralin. The cold traps, sodium pump seals, top shield, concrete cavity liner, and fuel storage cells are a few of the components serviced by the tetralin coolant system. A leak test is conducted on coolant piping. A fuel handling cask is provided for loading and unloading fuel elements from the core. An attached control panel, shown here as it is being wired, permits the operator to position the cask over the specified plugs for fuel loading and unloading. A full-scale mock-up of the fuel handling system, excluding the lead shielding, has been checked out on the test tower. The fuel hoist and electrical interlocks were operated through a series of tests in which fuel elements were raised and lowered an equivalent length of the core. Shown in this film was the fabrication and testing of major components for the sodium reactor experiment. It is anticipated that the experience gained from this fabrication, assembly, and operation will permit major improvements in reactor technology. This information will be incorporated into improved designs for full-scale sodium graphite power plants.
Information about the beneficial uses of atomic energy knows no national boundaries. The facts are available today, for nuclear energy isn't waiting to help people everywhere in some brave new world of the future. The peaceful atom is here now to serve what President Eisenhower has termed the needs rather than the fears of mankind. Nuclear reactors or atomic furnaces like this one provide the product that makes possible practical applications of nuclear energy. That product is the radioisotope, the atomic tracer, a common element tagged with radiation like a sheep with a bell. And because they are tagged, they can be traced, thus giving scientists, engineers, and doctors worldwide an invaluable tool for research and money-saving applications into biology, medicine, health, agriculture, and industry. In the past 8 years, the United States has made more than 47,500 shipments of radioisotopes to more than 2,000 users in this country and almost 3,000 shipments to 53 countries all over the globe at or below cost. Today, atomic radiation controls quality of industrial production, reduces industrial costs, achieves results hitherto impossible. Radioisotopes are at work today in the oil industry. Oil producers have the difficult problem of identifying each different batch of crude oil pumped from an oil field. Therefore, a small amount of an atomic tracer is added to the head of each new batch of crude oil at the field. Pumps force the radioactively tagged oil through pipes to the refinery. A radiation counter detects the radioisotope when it arrives at the head of each new batch of oil and automatically signals refinery headquarters. Savings, $500,000 a year. And the savings increase as the radioisotope is applied to oil prospecting, leak detection, and acidizing of oil wells. But petroleum is only one industry. Let's turn to motors and see how the tagged atom works there. Piston rings, previously made radioactive in a reactor, arrive at an engineering laboratory. The lead container stops dangerous radiations. One of the rings is then attached to the piston of an automobile engine. The problem is to measure how the piston ring wears in a test engine. When the engine is running, the piston ring rubs against other metal, causing tiny particles of the ring to wear away due to friction. These radioactive particles gradually accumulate in the engine oil. By measuring the radioactivity in the oil, engineers can tell how well the piston ring resists wear. Practical applications like these are already saving more than $100 million a year in American industry alone. Back in the engineering laboratory, instruments detect and measure the radioactivity in the oil. Before radioisotopes were known, tests for wear on moving parts had to be made by slow, inaccurate methods. Atoms from the radioactive iron are disintegrating and giving off bursts of energy. A radiation counter picks up these bursts of energy and a scaler counts them. Other radiation measuring instruments work automatically. Part of the machine records radiation counts on a tape. Several dozen oil samples can be tested for radioactivity in quick succession. Automatically, each oil sample is positioned and its radioactivity is counted. Factories now have an invaluable aid in radioactivity. In any process involving sheet material, paper or metal for instance, the thickness of the product must be measured and controlled with extreme accuracy. Using radioactivity, all this can be done without stopping actual production. In the base of the thickness gauging machine is some radioactive material. The sheet product blocks some of the radiation. The thicker the material, the more particles blocked. A radiation detector counts the radioactive particles passing through the sheet material. The thickness gauge employing radioactivity thus instantly measures any variation in thickness without costly interruptions to production. Industry saves millions of dollars yearly. To find dangerous flaws in metals or to test weldings, an X-ray film is attached to the metal. Radioactive material is taken from a lead storage safe and set in place to take a picture by exposing the X-ray film. Invisible rays penetrate metal, literally see into its heart, exposing the film. Since rays pass through flaws more easily than through perfect areas, the hidden flaws or faulty weldings are pinpointed accurately when the X-ray film is developed and a picture made. The tiny radioactive source can be spotted in tight or dangerous places where bulky X-ray equipment could not be fitted. Metallurgists, engineers, and construction workers have a new partner, an inexpensive partner, in the atom. But the atom is more than a symbol. Locked in its tiny nucleus is tremendous energy. In a piece of uranium the size of a walnut, there's as much potential energy as in the amount of coal to fill a 100-car train. The question is how to get this power, how to put this vast energy to work in the power plants to run the turbines of tomorrow. Here's one way. As uranium atoms in the nuclear reactor disintegrate, tremendous amounts of heat are generated. When the heat is transferred to a liquid, and the liquid is circulated from the reactor to a boiler room, it can produce steam. Steam drives a generator to produce electricity. And we are building such a unit today, the nation's first full-scale atomic power plant to produce 60,000 kilowatts of useful electricity, enough for a small city. It won't produce power economically competitive with coal or oil, but it is a major step in that direction, a big hope for the future. The future is the child of the past. And here at the experimental breeder reactor, known as the EBR, way back in December 1951 on an isolated desert in Idaho, was produced the first useful electrical power from the atom. These very motion pictures were taken with electrical power from the EBR, the first motion picture cameras ever driven by the products of nuclear energy. The operator brings the reactor up to power to gain the high heat to be transformed to electricity. This reactor is a forerunner of the machines which one day, with the help of the International Atomic Energy Agency, may provide abundant electrical energy in the power-starved areas of the world. Electrical power from the atom, for many years, may not be economically competitive in the United States, where fuel is plentiful. But with technical help from this country, economically competitive power reactors probably could be built in a much shorter time in high power cost areas overseas. Right now, out of these first nuclear machines, we're not buying power. We're buying knowledge, knowledge that we wish to share. The United States will open a reactor training school where scientists and engineers from abroad may learn the working principles of atomic energy. Now at the EBR, tremendous heat has been generated as the controlled chain reaction reaches a critical point. Heat is used to create steam, a process monitored by a trained technician. In the control room, steam pressure is watched. When it is right, a technician in the turbo generator room opens the throttle to let steam into the turbine. The drive coupling spins. Useful electricity has been generated by the atom. The desert is dark as the control room operator gets ready to shift from standard electrical lines to electricity provided by the atomic reactor. When he shuts the switch, all facilities inside the building, such as the machine shop, and all lights outside the building will be powered by atomic energy. Today, a bold experiment. In future years, a reality for homes and factories and schools all over the world. A beacon for the future, a symbol of hope. Now to the fields and farms of the world, where the atom means more productive farming at lower cost, more and better food for a hungry world. Nuclear research is finding more effective ways of using fertilizers, is producing stronger strains of disease-resistant crops, is fighting plant pests and diseases of plants and livestock, is studying the mysterious growth process that makes the food we eat and the coal and oil we burn. Botanists at a national laboratory where crops are grown under controlled radiation conditions gather valuable data on effects of radiation on plants and on future generations of plants. This work suggests ways of developing hardier, weather and disease-resistant strains of food crops. Altered plants may produce altered seeds, a cycle that may give new types of crops to the world. Yet how nature produces the food we eat is a fascinating mystery for atomic investigation. Photosynthesis, it's called. The process plants use in taking energy from sunlight and combining it with air and soil to make the complex food elements without which no life would survive on this planet. Investigators use atomic tracers to identify the complicated compounds produced by natural photosynthesis. Knowledge from this research someday may make it possible for us to manufacture food, synthetic gasoline, and coal. In special water-cooled greenhouses, atomic researchers grow many food and medicinal plants in a radioactive atmosphere. From these plants come the many compounds familiar to medicine and biology. The crucial difference is they are radioactive. They can be traced. From poppies, tobacco, and other plants come radioactive drugs, carbohydrates, acids, proteins, vitamins that are extremely useful today to researchers in medicine, biochemistry, physiology, and agriculture. So atomic farmers harvest radioactive crops that go to work for the knowledge of man's living environment. But the most immediate benefit of atomic research to the farmer is information on the most effective use of fertilizers. Botanists blend radioactive tracers with soil in order to study soil and plant nutrition. They have already established invaluable data showing where and how fertilizers should be placed for maximum uptake. When the plant uses the fertilizers most efficiently, what fertilizers are best for various soils, and how fertilizer is absorbed from the soil. This vital information is saving thousands of tons of fertilizer and millions of dollars every year for the farmer. At the same time, research produces data that may lead to better, stronger strains of plants. Similar tracer research is giving valuable information on insecticides and making definite headway against crop pests and the diseases of fruit and shade trees. Radioaction's use for food preservation and sterilization also is being investigated. But perhaps it's the atom's fight against suffering and disease that most strongly captures our imagination. Controlled radioactivity has placed us 25 years ahead in the battle against pain and death. Capturing the atom's probing power, science has found a powerful new tool to study and defeat sickness and make a healthier, happier life for the benefit of all mankind. The versatility of the atom in medicine is illustrated by the radioactive iodine atomic cocktail, which not only speeds diagnosis of thyroid cancer and other thyroid ailments, but also is effective in treatment of some types of cancer. Iodine concentrates in the thyroid, and when it is tagged with radioactivity, it forces the thyroid to reveal its exact condition. An amazing radiation counter actually draws a picture of the thyroid area to speed diagnosis or therapy. Radioisotopes, the greatest research tool since the microscope. Cancer research goes forward all over the world with radioisotopes distributed at only 20% of cost. But cancer isn't the only disease under atomic investigation. Brain tumors, hyperthyroidism, leukemia, and other blood diseases, hardening of the arteries, heart disease, virus infections, diabetes, circulatory diseases, anemia, nervous and mental ailments. All are slowly giving up some of their intimate secrets to science with the aid of atomic energy. We go into New York's Montefiore Hospital to see a powerful aid in the fight against disease, the Cobalt Teletherapy Unit, which was developed and is being improved by cooperating scientists all over the world. With a sharp, effective beam of atomic radiation, which does not injure healthy tissue near the cancer, the nuclear tool bombards deep-seated tumors with a stream of invisible rays, billions of particles of energy similar to X-rays, but much stronger. Tumors shrink and cancer cells are destroyed as this one machine gives off more radiation than all the medical radium in the world. No cure-all, final results will take time to evaluate, but a big step forward in cancer treatment. In a message to the Atoms for Peace exhibit in Rome, President Eisenhower said that history will one day record as the most far-reaching physical accomplishment of the century, or even of 20 centuries, the discoveries which in recent years unlocked for the use of mankind the boundless energy of the atom, the versatile, peaceful atom that promotes agriculture, fights disease, provides valuable radioactive tracers for science and industry, that is the basis for future economical power for cities, homes, and factories. America, as President Eisenhower pointed out to the United Nations, deeply desires to join countries all over the globe in adapting the atom to the arts of peace.
The lure of the unknown has always been a tremendous challenge to man. We look with awe at the stars and wonder if we will ever reach them. We marvel at the miracles held in a single drop of blood. Yes, the same quest for knowledge that points us towards the magnitude of the cosmos also leads us to the infinitesimally small. Man has always wanted to probe deeper into the smallness of things. It has been part of his great curiosity about matter itself. Since antiquity, scientists have been striving to find the elementary particles of matter, the basic building blocks of everything around us. The ancient Greeks even gave a name to what they thought of as the basis of all matter. The atom, they called it, meaning something that is indivisible. They never dreamed that the fantastically tiny atom contains a complex world of its own. The optical microscope makes it possible to see a living cell consisting of millions of atoms. The electron microscope takes us deeper into matter, and we may see a virus composed of thousands of atoms. But if we want to delve beyond the limits of the microscope in the search for the atom itself, then we must use powerful new tools and instruments. The particle accelerators, known popularly as atom smashers. Let's go into the control room of an atom smasher. What is an atom? How do we know that it too has parts? How can we see it, smash it, identify its components? We know today that there are at least 103 elements. It is the combination of 92 of these elements into molecules that accounts for all the compounds that are common to our experience from A to Z, from aspirin to zinc oxide salve. But every element has its own atomic structure,
An atom is something like a tiny solar system with a nucleus of electrically neutral neutrons and the electrically positive protons. For every proton in the nucleus, there is always a planetary electron. Electrons are electrically negative and so light that it would take 1,840 of them to equal the weight of a single proton or neutron. Despite its small size, the atom is mainly empty space. If an atom were expanded to the size of the giant Dodger Stadium, the tiny nucleus would be about the size of a housefly. The number of electrons and their flight path around the central nucleus determines the chemical properties of the atom of the particular element. So the 103 elements are not really the elementary building blocks of matter. Within their atoms are nuclei, and around these nuclei are orbiting electrons. Every element has its own specific number of electrons. But the discovery of the structure of the atom didn't satisfy the scientists either. Following the atom smashing of the early 1900s, scientists started chipping away at the tiny nucleus. This period of scientific study was capped by discovery of nuclear fission, or splitting of the nucleus, the keystone to all future atomic progress. Breaking open the nucleus with a so-called atom smasher made it possible, in effect, to see and study the atomic nucleus. With the newer accelerators in the 1950s, smashing the particles in the nucleus became possible, and physicists began to learn about the dozens of new elementary or subnuclear particles. We use the word see loosely, for man may never really see an atom, let alone its nucleus or the subnuclear particles. But we can recognize and study the nuclear and subnuclear particles by their tracks. A bubble chamber with a camera is designed to make these tracks show up. It is one of the most amazing research tools of all time. The incredibly small elementary particles are produced by electrons or protons accelerated to incredibly high energies by these machines. Hence the terms elementary particle physics or high energy physics. The tinier the particles of matter, the bigger the machines needed to probe them. Because the further we delve into the sub-levels of nuclear structure, the more powerful are the forces of energy, binding together the subnuclear particles. Let's look at the atom smasher, its basic components, its way of operation. It takes a diamond to cut another diamond. Also, it takes an atom to smash another atom. This is the theory of the atom smasher. The process has many things in common with the firing of a cannon. There is a barrel, a projectile, a charge, a target, and an observation post. The projectiles of an atom smasher are particles of the atom. For example, protons or electrons. It is necessary to separate the projectile particles from their atoms if they are to be used as bullets. Electrons are gathered from a hot wire as in a radio tube. Protons are obtained when the electron is stripped from the atom of hydrogen. The hydrogen nucleus is a proton. Now that we have the projectile, we have to find ways to shoot it. The atom smasher or particle accelerator uses electromagnetic attraction and repulsion in the place of powder. Charged particles are repelled by the like electrical charge and attracted by the opposite charge. The energy depends on the nature and amount of the electrical charge or the strength of the magnetic field. The common unit for energy is the electron volt. It corresponds to the energy acquired by one electron charge passing through an electrical potential difference of 1 volt, a unit of energy comparable to the foot-pound. Light atom artillery produces particles with thousands of electron volts. Medium artillery, particles with millions. Heavy atom artillery, particles with billions of electron volts. The accelerated particles, or bullets, need a barrel to give them direction towards the target. Atom smashers use different sorts of barrels to propel or accelerate the particles. This acceleration process gave atom smashers the name accelerators. The atomic bullets may be shot in a straight line or within a circular chamber. In a linear atom smasher, the acceleration may be accomplished within a single acceleration chamber, as in this Van de Graaff unit, or in this Cockcroft-Walton accelerator. The machines bear the names of their inventors. Or the acceleration may be accomplished in a number of consecutive sections. This is the 2-mile-long linear accelerator at Stanford, the largest of its kind in the world. It houses an absolutely straight 2-mile-long copper tube with a diameter of only 4 inches. The projectiles are electrons. During their 2-mile trip from the injection area to the target stations, they are accelerated to an energy of as much as 20 billion electron volts. At the far end of the accelerator, another 1,000 feet is used by a beam switch yard, which directs the electrons into selected target areas. A different acceleration method is employed in the cyclotron, the invention of the late Dr. Ernest O. Lawrence, founder of the Radiation Laboratory at Berkeley, pointing to the 4-inch acceleration chambers of his original cyclotron. A charged particle in motion is influenced by a magnetic field. This field will bend negatively charged particles in one direction, positively charged particles in the opposite direction. This fact made the cyclotron and more advanced accelerators possible. In a cyclotron, the atomic bullets are inserted in the center and exposed to 2 powerful forces: a magnetic field from 2 mighty magnets and a rapidly alternating electrical force. The particles gain speed and travel in an ever-widening circle until they near the outer edge. Here they are drawn out of the chamber by a deflector and emerge as a beam of high-energy atomic projectiles. In other circular accelerators, the atomic bullets speed around as on a racetrack. They are held in place by powerful magnets and are pushed and pulled by radio frequency electrical forces until they almost reach the speed of light, 186,000 miles a second, the speed limit of the universe. These accelerators are exemplified by the Bevatron at the Lawrence Radiation Laboratory on the West Coast, which develops 6 billion electron volts, by the giant 33 billion electron volt synchrotron, the AGS, at Brookhaven National Laboratory on Long Island, an atomic racetrack 1/4 mile across, the highest energy accelerator in the world. And in the planning stage is this 200 billion electron volts monster, 1 mile across, 3 miles around, a $300 million project. These giant atom smashers need a smaller accelerator as a starter to give the atomic bullets their initial push. The atom smashers produce a stream of high-speed projectiles, which consequently are tremendously powerful projectiles. This barrage is aimed towards targets, the nuclei of other atoms. The ultimate targets, atomic nuclei, may be in a stack of photographic film, in a metal disc, or consist of the atoms of hydrogen in a liquid hydrogen bubble chamber, a giant piece of equipment answering to this colloquial term. All the tremendous effort that goes into an experiment is expended in the hope that one of the millions of atomic bullets may hit one of the millions of target atoms. Should that happen, the observation posts will be on the lookout for new types of tracks that may lead to the discovery of another elementary particle or a better understanding of the basic structure of matter. Photographic plates which have been bombarded by particles are being analyzed for such tracks. The bubble chamber, such as this movable 72-inch unit at Berkeley, is now becoming one of the most successful observation posts. It contains liquid hydrogen. The smashing of a hydrogen nucleus will leave tracks in the liquid hydrogen and reveal this strange world of invisible ammunition and invisible targets. The tracks are like the vapor trails of jet planes. The vapor trails reveal the presence of an aircraft that is otherwise invisible. A camera keeps a continuous record of the activities inside the bubble chamber. Many thousands of exposures from the camera are examined in the search for new, elusive bits of information. What is the purpose of these multi-million-dollar projects? Atom smashers already find many practical applications. They produce radioactive isotopes, atomic tracers used in industry and medicine. Their powerful beam may be used to fight cancer in this painless and bloodless operation with what has been called the atomic knife. But most atom smashers serve pure research. They continue our search for information, the search for new elementary splinters of the unknown, the search for the powerful cosmic glue that holds all matter together. By using atom smashers, scientists someday may learn the mysteries of the basic nature of matter and the laws that govern our universe through the magic of the atom.